Statistics Week 8, Part 5. Try this example based on the information at the end of the last video. Stop the video, and when you're ready to see the result, start it again. (8.5) Refer back to the pizza delivery triad exercise. The mean delivery time is 36 minutes and the population standard deviation is 6 minutes. Assume the sample size is changed to 50 restaurants with the same sample mean. Find a 90% confidence interval estimate for the population mean delivery time. So in this case, the mean is again 36, and the confidence interval with sigma equals 6 and n equals 50 is 90%. So we calculated the 90% confidence interval before, and we'll do that in the same way here. So that CL is 90%, alpha is 0.10, alpha over 2 is 0.5, Z of alpha over 2 is Z 0.05. So that's going to give us an area to the left of 0.95, and using inverse norm on 0.95 with the standard normal distribution gives 1.65. So find the error bound, EBM. That's going to be 1.65 times 6, the standard deviation, over the square root of 50, which is 1.40. That gives us a confidence interval of 34.60 to 37.40. If we interpret that, we estimate with 95% confidence that 90% confidence that the true population mean delivery time for all pizza deliveries is between 34.60 and 37.40. Another thing we can do is working backwards to find the error bound or the sample mean if we know the confidence interval. Sometimes when we read statistical studies, the study may state the confidence interval only. If we know the confidence interval, we can work backwards to find both the error bound and the sample mean. Finding the error bound. From the upper value of the interval, subtract the sample mean. Or, from the upper value of the interval, subtract the lower value, then divide the difference by 2. Of these two methods, usually the second one is more universally applicable because oftentimes you do not know the sample mean. You might know the sample standard deviation, so the second one is probably going to be more useful. Finding the sample mean is similar. We can subtract the error bound, which we could get from the previous calculation, from the upper value of the confidence interval, or average the upper and lower endpoints of the confidence interval. This is almost the same calculation as the second calculation for finding the error bound, except we add the upper and lower bounds together and divide by 2. In general, the second method for both of these is going to be the method that you use because it's simple to apply and you don't necessarily know the mean. Here's an example. Suppose we know that the confidence interval is 67.18 to 68.82 for some data set, and we want to find the error bound. We may know that the sample mean is 68, or we may not. Or perhaps our source only gave the confidence interval and did not tell us the value of the sample mean, so we'll calculate both ways. To calculate the error bound, if we know the sample mean is 68, we can go upper value, which is 68.82, minus 68 is 0.82. Alternatively, if we don't know the sample mean, we can simply subtract the upper bound from the lower bound and then divide by 2 to get 0.82. It's easy to use a little bit of algebra to show that these two answers come about for a definite reason. Calculate the sample mean. If we know the error bound x bar, we can subtract 0.82 from the upper bound and get 68, which is the sample mean that you can see above. Alternatively, we can simply average those two by adding the lower and upper bounds and dividing by 2 and getting 68. Again, it's easy to show by algebra that these two answers are the same because the calculations are essentially the same. Here's an example you should try. So you can stop the video, try this, and then start it again when you want to see the answer. Here's our solution. 8.6. Suppose we know that a confidence interval is 42.12 to 47.88. Find the error bound and the sample mean. Since we do not know the sample mean, we're going to add 42.12 and 47.88 and divide by 2 to find it. The sum of these is 45, so that's the sample mean. Now, for the second part, since we did not know that the the sample mean to start, subtract the lower interval value from the upper interval value and divide by 2 to find the error bound for the mean. So this gives us 2.88, the error bound for the population mean. And you can easily see that if you add and subtract 2.88 from 45, you get 42.12 and 47.88. Calculating the sample size for a specified margin of error is another important task. It's often necessary that we have some data to study. We have a study that we want to perform. We want to be able to get the correct sample size to ensure that our confidence interval will be accurate. So the formula for sample size is n equals z squared sigma squared over the error bound squared, or more simply, just n equals z times sigma over EBM, the quantity squared. This is found by solving the error bound formula for n. In this formula, z is actually z of alpha over 2, which corresponds to the desired confidence level, as we did in our previous calculations. When you want a specified confidence level and error bound, you can use this formula to calculate the size of the sample needed for the study. Here's an example. The population standard deviation for the age of Foothill College students is 15 years. If we want to be 95% confident that the sample mean age is within 2 years of the true population mean age of Foothill College students, how many randomly selected Foothill College students must be surveyed? Well, we need to gather some information together for this. The first task in our solution is we know that sigma is 15, the standard deviation. We also know that the error bound is 2. We have to dig that out here, but if you look carefully, the within 2 years of true population mean age is our error bound. Also, we know that we want a 95% confidence interval, so for our previous calculation, that would be a z-value of 0.025, which is 1.96, because the confidence level is 95%. We can now apply our formula. The value n using the formula is n equals 1.96 times 15 divided by 2 squared. That gives us 216.09, or about 217. We round that value up to assure that we will have enough data in the study to make our confidence interval accurate. Therefore, 217 Foothill College students would be surveyed in order to be 95% confident that we are within 2 years of the true population mean age of Foothill College students. To test what you've learned, you can try this triad exercise. Then turn the video back on when you are ready to see the result and check your answer. 8.7. The population standard deviation for the height of a high school basketball players is 3 inches. If we want to be 95% confident that the sample mean height is within 1 inch of the true population mean height, how many randomly selected students must be surveyed? Since we know the confidence interval should be 95%, and we want the error bound for the mean to be 1, when the population standard deviation is 5, we first need to compute the z-score for the 95% confidence interval. From previous examples, we know that for a 95% confidence interval, we have z 0.025 is equal to 1.96. Then, to find the sample size n, we'll simply use the formula, so n will be 1.96 times 5 divided by 1 squared, which is 96.04. So our sample size should be 97.